sure the title screen will pop up in a moment. My name's Gary Boorman. I'm currently employed by Royal Holloway. Sorry, if I plug this in, that would help.
It's not wireless yet.
Not wireless yet, no. We'll be on in a moment. Yeah, I'm currently employed by Royal Holloway, University of London, but I'm actually working at CERN. I've worked at CERN for a couple of years, and recently 2 colleagues and I have set up a company based in Geneva called Angara Technology. We're doing LabVIEW from the sensor to the database, kind of all the electronics, all the FPGA, RT, and all the LabVIEW in between, and any other bits of glue, Python, whatever that we actually need. So I'm going to talk to you about signal acquisition, the practical guide. All of you are really good at wiring in LabVIEW. My experience from going around CERN and other labs is that not everyone is very good at wiring using physical wires, this sort of thing. So I'm going to show you what goes wrong, where the problems are, and also how to get it right as well. I've got a NI virtual bench. I don't know if anyone of you have seen the virtual bench. Very popular in universities. It's an all-in-one box, scope, signal generator, and so on. DMM, logic analyzer. So why do I need to worry about all my signals? I'm only collecting data at 1 hertz. What can possibly go wrong? Are there any T's in your signal lines, in your trigger lines? You know, you've got these little BNC T's here. Have you got any of those? Is there somewhere you're using some unshielded cable to actually connect your signals? Do you have small signals? Generally small in this sense is less than 1 volt. Are the signals periodic or do they appear randomly? Do you have odd behavior when you're actually acquiring your data, things you can't really explain? Have you gone to the extreme of adding some filtering to try and get all these signals looking correct when filters were never originally part of the system? The one I like, does the system still work if you start wiggling your cables? I would say always, always perform that test. If you wiggle a cable and something changes, possibly your cable is wrong or your connection is broken somewhere. Always do that test. So this is what we're going to sort of discuss today. Impedance. Okay, I know many of you have gone to university to study some engineering type subjects. So you're probably all familiar with impedance, decibels, how to actually connect cables properly. Crosstalks, bandwidth, how to do triggering. Then we get on to the bit that's something to do with the title of the talk, the actual signal acquisition. If I show you how to get it all wrong to start with, I'll also show you how to do it correctly. And looking at some about what the actual ADC parameters are. Now I've got my virtual box and you actually get a scope view and function generator view on the screen. And I will show you how to connect things in different ways, how to make problems for yourself. Those of you that have been to my talks before know I always have rules of thumb. What are the bits you actually have to take away from this to actually make it useful? My first rule of thumb is always use a rule of thumb wisely. Try and know when to apply it and when not to apply it, when you actually need to do the real maths. I'm going to quick summary of impedance and matching. Impedance is basically an opposition to a flow of energy. Sometimes, depending on the equipment, it's a function of frequency as well. So it's a non-constant impedance with respect to frequency. If you match things correctly, you've probably all seen this from university. If you get your source impedance, your characteristic impedance of your cabling, and your load impedance, if you get it all to match, you get maximum power transfer. What that means is your signal is going to be, what comes out of your signal source is actually going to be what appears at your signal sink on the right there. If you don't get your matching correct, things start to go wrong. Cable lengths, when you're talking about electrical cables, okay, a cable has to have a length to get from A to B, but it's also often defined in terms of its propagation delay. So, I mean, a lot of these cables have little labels on, tells you how long the average signal takes to propagate down that cable. Long and short cables. When you start to deal with signals, a long cable is anything really greater than lambda over 10. Lambda's the wavelength in the actual cable of interest. As an example, if you've got a 100 megahertz signal going down RG58, which is the standard lab cable that you have using the formula there, you can work out that lambda over 10 is in the order of 20 centimetres. Treat your cabling as a transmission line. Now, I'm not going to go into the theory of any of this. I'm going to demonstrate it instead. Where's it gone? Just have to reset this. It'll pop up in a moment. What I've got on here is a function generator. I'm just generating a square wave or a pulse at... They'll sort it out. It's generating a square wave at 5 megahertz with a fairly sharp edge to it.
Ask him to wiggle the cable.
Yes. Yeah. If it doesn't work, wiggle the cable. And then there's... there we go. Thank you. So I've got my 5 megahertz signal source there, and there's an oscilloscope as well, and I've just got a short cable, about half a metre or so, and I'm just generating the output there. You may be able to see that I've got a slight wiggle on here. This system is not a matched system. I've got no termination on my load there. So I've got a selection of T's. This particular box doesn't have 50 ohm inputs on it, so I have to do it using a little T here, but I'm putting it right next to the input. And hopefully you can see there that my little wiggle has disappeared. Okay, you may not think that's overly impressive, overly important right at this moment. But those little wiggles, if you're triggering on that level, so if we take the terminator off, if we were triggering, say, at a level round about here, it's possible we could end up with some double triggering, depending on the length of this cable. So I can put in a different length of cable. Let's just use slightly longer, and you can see that my little dip is actually moved along by some nanoseconds there. It's actually the time, because what's happening is the signal is reflecting. This is now no termination. So the signal comes out, hits effectively an open circuit, and gets reflected back to the signal source, and it comes back again, and so on. I mean, many of you are familiar with this type of idea. Let's go back to the presentation. I've done that one. Matching, generally, if you get it within 10%, you're going to have no problems at all. So 50 ohm systems, the standard for the labs. If your impedance is somewhere between 45 and 55 ohms, you won't have any problems. When you start to do mismatching and discontinuities, we've currently got an open circuit on here. You get reflections, and basically they're in phase with the system. Short circuits, I'm not going to short circuit this one because I don't know what will happen, the output if I do, but try it on someone else's equipment, a short circuit will reflect at 180 degrees. And discontinuities is basically a change of impedance, and you can get partial reflections. A really easy way to do that is to start abusing your cables. You bend them far too tightly, you tread on them, you trap them in cabinet doors and so on. Okay, you've only paid €3, pounds, francs, whatever it is for a cable, but that small amount of money might end up causing you problems in the long term. All of this is based on real experience. Most of it not mine, most of it other people's. If you've got RF stuff, just be very careful. Some RF sources do not like driving into an open circuit, and they like driving into a short circuit even less. So before you output enable or turn it on, whatever it is, always make sure you've got the correct load on your output source. Don't tread on cables. It will ruin them, basically. I've been in labs where you have cables all over the show, people dancing up and down on them. They've got signal problems. You come along, you look at the cable, you measure that one cable, give it the wiggle test, and you tend to find a problem. So you've got to be really careful. Decibels, I'm not going to spend too long on decibels, just because I haven't got too much time. Decibels are very common to describe signals in particularly the RF world, but also in the lab as well. Gain, attenuation, loss, whatever it is always or usually expressed in decibels. This is what I often present to students. But this table on the right here, this is the useful one. I mean, I deal with this all the time. I just know what these things are. 3 dB is a doubling in power, or multiplying or dividing by 1/√2 if it's dealing with voltage. I pin this table up somewhere near your workspace. I find it very useful. And just for a point of interest, RF is usually dealt with in dBms, which means a gain or a loss with respect to 1 milliwatt of power. I mean, all the RF people in the room will just know that anyway. But again, you often see it, if you've got a PXI signal source, you will often see all the specifications expressed in dBms. So if you want to go to dBm, your power ratio there, it's all with respect to 1 milliwatt. So 0 dB is 1 milliwatt, 6 dB is you multiply it by 4, so you've got 4 milliwatts. Coax cables, almost always they are 50 ohms. If you buy them from RS, Farnell, whatever, it's hard not to buy a 50 ohm cable. But just be aware, if you are in this world of the TV, satellite, all the high sensitivity receivers and so on, it's often 75 ohm. All of the video equipment in here would be 75 ohm. Every time a signal goes down a cable, some of it gets lost through resistive heating. And if you look at your data sheets, when you buy your cables, you will see figures rather like this, X number of dBs per 35 point meters loss at a particular frequency. 30.5 meters, okay, it's not a unit that I tend to use, but all the Americans will know that that is 100 feet. All the cabling that comes across the Atlantic it's on drums of 100 feet for some reason, I don't know why. Anyway, there are different sorts of cables you get. RG58, this is the real workhorse, this in the labs. It's good for most things. It works up for hundreds of megahertz. If it's a short cable, it'll go even further. And there's different sorts of cable. There's 174, that's like 3 millimeters, easy to bend, but higher losses. The 213, it works at a higher frequency, but it's 3/8 of an inch, 10 millimeters. It's harder to bend things. It's harder to get set up, but it's handy just because you don't have so many losses. Good for a longer signal run. And a really good rule of thumb, signals travel at 5 nanoseconds per meter in coax cable. So if you've got a 2 meter cable, you've got a 10 nanosecond delay. I will just show you the effect of some of these different impedances and how to get things wrong. Now, this is 50 ohm cable. I can actually add in another section. I was really looking hard to find some 75 ohm cable, and I actually found a piece by accident when I was at CERN, and it came off a bit of equipment, and probably somebody had problems but without realising it. So I've now got a 50 ohm and also going into the 75 ohm before it gets to the end. And you can see the effect of this discontinuity. I've now got a waveform that is quite distorted, even more than it was before. This is unterminated at the moment. And you can see I've got overshoot, I've got undershoot. This is because this signal is being partially reflected at the interface between the 75 and the 50 ohm cable. So when you've connected your test equipment, you've got your signal coming in, You've got your signal coming in. Make sure that you've got your cabling correct. And if you see things like this, if it's not what you expect, check your connections, check your cabling, just make sure it's correct. If you're trying to trigger on something like this, then, okay, you can set a trigger level. It gets even worse in a minute. I'll show you how to make these signals look even worse. And this is not just an academic exercise. This is unfortunately based on reality. So the 50 ohm termination. I've got a selection of 50 ohm terminators. You can put about 1 watt into these before they get too hot. Some equipment has 50 ohm termination built in, some doesn't. This one doesn't. I have to use a little T. Generally, always make sure your signals are terminated correctly. Yeah, sometimes they're external, sometimes they're internal. If you are using an external load, terminate it using your T as near to the signal sink as possible. I know I've still got 75 in there, but I've now got a termination on there, and we can have a quick look at the there. It's actually cleaned up this signal really well. I mean, there's a few little wobbles in there because of this 75 ohm, but generally it's looking a lot better because of this termination. I could put the termination somewhere else instead. I could actually put it somewhere halfway along here. I wouldn't recommend doing this, but you can do it. So you can do things like that, and you terminate halfway along. I'll demonstrate that live in a minute, but I can assure you it's going to cause you problems, because effectively, the far end, rather than having your termination resistor there, you've got terminated halfway along, then you've got a T with a nice length of cable that is an open circuit. So you're going to get a reflection coming back again, and it's going to then mess up the signal that you're actually reading at where your T is. I mean, I could connect my scope on here. Yeah, there's lots of ways to get it wrong, and people have found most of the ways, actually. So you can use a T. As you know, some things have selectable input impedance, scopes, and so on. Sometimes they're selectable. Some DAQ-cards as well. It depends how much you've paid as to whether you get the 50 ohm input or not. Generally, you pay more money for that bit. And if you are using oscilloscope probes or DAQ-card probes on high-frequency stuff, be aware that as soon as you start probing high-frequency circuits, what you measure is not reality, because you've got all this extra impedance and all this opportunity for extra reflections to go on there. So, splitting a high-frequency signal using a T, let's make sure I've got enough time. Splitting the signal can cause problems even if you terminate correctly. When I say correctly, what's happening? If I've got a signal source and I've got nice 50 ohm cables, and halfway along I then put a T, I'm losing track of what I've actually got here at the moment, but I've got my signal. This is coming out of my signal source. Let's put a T on here. And then one side goes to the scope, the other side. So I'm making a T, and I've got some other imaginary bit of equipment on the end of this cable. What's going to start happening to this signal here? It's actually dropped too much, so I've got to reset my triggering level. Where's it gone? It was here a moment ago. Let's take it off for a moment. connect it onto the right channel. That'll help. There we go. So you can see I'm now looking, I've split my signal with a T, one end going to the scope, the other end to some other imaginary bit of equipment. And look what's happened to my waveform. It's gone all over the place. And that's because you're getting reflections going back and forth along this cable. And you get constructive and destructive interference going on, and you can see what's happening to the signal. Now, there are ways of doing this better. Let's go back to the presentation. If you really need to split a high-frequency signal, do it something like this. Make sure that you've got your termination at one end and a really short, a T on the device of interest. So if I was to change this around a bit, so rather than splitting in midair, I'm now going to split the signal. So I've got the signal coming out. It's going to a T right next to the input. So this is my signal sink number 2. And then over at the end here, I would connect this to my other terminated bit of equipment. And that's kind of the best you can actually do. Never split signals with any length of signal, any length of cable either side. Or you can use one of these devices, a proper 50 ohm splitter. This actually is all nicely matched, so you won't get any reflections. But because you're splitting the signal, each output is half the power goes to each output. So the voltage actually drops by a factor of it's a factor of 0.7 of what comes in. But if you know that, because you've got a good quality splitter, you're not going to actually have any problems there. So my rule of thumb is don't split things with a T. You're asking for problems. And I've seen it all before. So here's my scenario. Unfortunately, based on reality, not my reality, the colleagues. So I start with my nice reference system. I've got some analog signal source. It's got a nice 50 ohm cable, and it's got a 50 ohm with a little T on the bit of equipment of interest that I'm actually acquiring the data on. Somebody comes along, and they put in a T, rather like we've got here, to our oscilloscope. Okay, things are still working. Okay, it's on the high impedance, the high Z input. Someone then moves the scope from the bench up onto the top of the rack, and they think, this cable doesn't reach. I'll just put a 2 meter bit of cable in from the T to the scope. We've seen what happens when you do that. Another T is added into the system because someone else wants to use this signal to perhaps do some another digital input to do some triggering, something like that. They then terminate it to 50 ohms. So we've now got two 50 ohm terminations. So we've got the mismatch because it looks like 25 ohms, but we've also got all these reflections then going on because you've got a mismatch by a factor of 2. The first trigger stops working because of this. It's terminated twice, the voltage has dropped, so you increase the output level of your analog triggering source. All well and good. Unfortunately, someone else comes along and splits the signal yet again and adds a 10 meter cable. You get a nice long reflection. 10 meters is 50 nanoseconds. The transit time is double that because it has to go there and back. So you've got a nice another 100 nanoseconds later, you've got a really nice reflection. If you're using that as a trigger, you may end up triggering twice because you've got your original signal, 100 nanoseconds later, you've got another edge there. So you've got this double triggering. So, bright idea, let's add a filter. It's been done. You might laugh, it has been done. And this reduces the signal level yet again because of the filter. You've got input loss. So you increase your analog output level again. You're already at the limit. Right, you need the next analog source, so you need a higher input or higher output range for it. And so it goes on. This is unfortunately based on some reality at CERN in one of our test labs. It happens. A system that originally works, someone thinks, I'll just add a T in, add a bit of cable. It's electrons, they don't care, they'll be fine. Unfortunately, it does matter. So, and hopefully I've demonstrated that. I mean, if anyone wants to come and play with all this stuff, I can set it up outside. If you want to try all the effects of these different things, adding T's, impedance, different impedance cables. We've even got a cable, so we can do unshielded cable. We can do it all. So they're the big problems, and I think you know how to solve it. You've got to think about your cabling. So we're going to talk about crosstalk. How are we doing? So crosstalk is where you've got a signal travelling down one cable and it induces some current and therefore voltage on another cable or another circuit. Stray electromagnetic fields. If you've got a changing field, you induce a current. So schematically that's shown. So along the bottom, you've got what's called your aggressor circuit. You've got some signal there that's actually driving some edges there. So you've got a change in field, and that will induce a change in current. I mean, this is capacitive coupling. This is the most common way of doing it, just by having your signal cables side by side. And where you get a change in voltage, you get a change in field, and that induces current and voltage on this top circuit, the victim circuit there. Sometimes that voltage is quite small, you don't care. Sometimes it can actually then be big enough to trigger something or create an effect that you don't really want. How can you actually avoid all that? Don't put things in parallel. That's always the golden rule. If things do go in parallel, space them apart. The field is proportional to the square of inversely proportional to the square of the distance between them. So you don't want high sensitivity thermocouple cables running next to some large switching currents on a motor or a high-powered valve or something. Avoid all of these issues. Keep signal cables well away from power cables. And also, if you need to cross cables, cross them at 90 degrees rather than sort of running slowly in a very slow crossing, because the crosstalk is proportional to the cosine of the angle. So if they cross at 90 degrees, in theory, there is no crosstalk. In reality, there's a very, very, very small amount, but don't worry. The kind of things that effects of it you will actually see is if you see a 50 hertz signal, that's from mains. 100 hertz is usually from fluorescent lighting. Motors and switching, okay, that's broadband. Particularly once brushes on motors wear out, you get a very broad band of noise. 40 kilohertz to 80 kilohertz, sometimes a bit more. Switch mode power supplies. You can see all of these actual effects there. So when you look at your signals and you're seeing something like this, these are the likely sources. So you know to try and perhaps route your signals, whether it's some acquisition signal, clock signal, trigger, whatever it is, route it away from these noise sources. The signal bandwidth. I mean, I mentioned at the start of the talk, I'm only acquiring data at 1 hertz. Why do I need to care about all of this stuff? Signal bandwidth is actually quite important. This you probably know, sine wave is a pure frequency. It exists at one point on the spectrum. And a square wave, you can represent that by a Fourier series of the harmonics of the sine waves. The rise time of your signal is basically set by the highest harmonic you have available. And by harmonic, I mean it's a multiple of your fundamental frequency. So when we looked at the scope there, the speed of the edge, the rising edge, is basically set by the bandwidth of the system there. If you've got a low bandwidth, you can only get very slow edges. So you need a high bandwidth for faster edges. For accurate triggering, you need fast edges. So we're putting in a pulse because it's going between 0 and some voltage. But you probably all know what these are looking at. This is like a square wave. So you've got the fundamental, and you've got all these harmonics. And they actually, to get a reasonable square wave, you need to go to a fairly good number of harmonics there. So to get this rise time, and the full time as well, you need to maintain the bandwidth of your system. So how much bandwidth do you actually need for this? The really good rule of thumb is the bandwidth in gigahertz is 0.35 divided by your rise time. So if you've got a rise time of 10 nanoseconds, 0.35 divided by 10, is 0.035 gigahertz, 35 megahertz. This is one I use all the time, just to make a really good estimate of what bandwidth do I need. If I'm trying to use an ADC to measure a square wave or a pulse, something like that, what's the bandwidth I need? I can use this formula, and that, to a good approximation, will work. So if you know something about the signal you want to acquire, this tells you how much you need to spend on your ADC to actually get sufficient rise time. Look through the ADC specs, and it tells you, bandwidth, X megahertz, or X number of hundreds of megahertz, whatever it is. So we looked at these signals here. We've got a very rule of thumb, I think, is essential. So the triggering. Digital triggers generally fall into one of two categories, edge-based or level-based. It's like event-based or polling. The ideas are interchangeable between LabVIEW. I've said LabVIEW, and electronics. There is no LabVIEW in this talk, actually. But make sure your trigger edge doesn't have any glitches. Make sure you've not got these problems that we've set up before here, where you've got reflections coming on various cables, because it may be that you multiple trigger. And how does it occur? Because of an impedance mismatch. It all goes back down to impedance. Analog triggering as well, again, you can suffer from noise. I mean, noise picks up from various sources. A couple of slides before, we've got all the different noise sources, switch mode, power supplies, mains hum, and all the rest of it. How do you get rid of that? Well, okay, you've just got to pick some threshold. You can also use this function called hold off. So after a trigger, wait for a certain time before you then arm your trigger again. Often, I find analog triggers are for non-periodic systems. My world is like accelerator-based engineering. Accelerators, particle accelerators, are by their nature periodic, but as soon as you go to the nuclear experiments, everything is then random, completely random. So you can use analog triggering for that. So the trigger problems, well, the first of it, don't get a problem. Make sure your cabling is correct. You've got all the little toys to play with here. And ensure your setup and hold times are met. So if you've got a trigger at the right time for a particular signal, make sure your trigger actually comes in when you need it, not slightly delayed. And there's also, you'll find setup and hold times in the data sheets of all of the DAQ devices. So if I want to look at, say, this edge on a clock here, I need to make sure that my trigger comes in sufficiently before it. Skew, if you're triggering multiple devices, you want to make sure that they trigger when you want them to trigger, so you've got to make sure that you distribute the trigger signals with appropriate impedance cabling, and make sure the cabling has the same electrical length if you want these two events at the same time. Same with clocks as well, triggering clocks. You're distributing a signal, it's got to be synchronized. Generally the solution is, if you want to make your triggering work, assume you've got good cabling, add cable rather than take cable away to actually get everything to align. Ground loops. This is now coming on to all the ADC stuff. This is, I find, the bit that most people gloss over. So a ground loop, the definition I picked out from Wikipedia, the interconnection of electrical devices that results in being multiple paths to ground, so a closed conductive loop is formed. Now this diagram here, commit this to memory. If you look, say, from the earth point down the bottom center, these are the power pins, so like, say you've got live, neutral, and earth on the left and the right there, and your signal source, your signal sink, they share a common ground. And what you'll find is you've got a turn, or one loop of some conductive material. It's usually the wire, made up of the earth wires from your equipment, and then perhaps that using your BNC, your RG58 cable, nice shielded cable, that completes your ground loop. When you get a loop, you can get mains wiring particularly is really good at inducing a current in that loop, because the mains electricity is continually changing at 50 hertz. So you've got a changing field in inducing a current. And as we're not in the world of superconductors here, you have a resistance and a current, you'll get a voltage drop across that resistance. And that voltage ends up being added to your input there, your ADC input, perhaps. So this is, I'd say, probably the most important diagram here in the presentation. This is what a ground loop looks like. This is what it means. It's also, you can view it as like a turn of a transformer. And if you link a circuit of a transformer with another one, you've got the iron core to actually, you can actually link another loop through there. And with mains wiring, it's quite light. You've got a loop through there. You will be inducing all sorts of currents. And I'm sure you've all seen 50 hertz pickup on a ADC. Okay, you can sample at 50 hertz and that gets rid of it. That's one way to do it, to solve the problem. But look at the back of all the ADC datasheets that come from NI, and they actually tell you what to do. You've got to, in essence, break the loop. You've got to break the ground loop. And there's lots of ways of doing it. So for instance, this one, it's exactly the same diagram, but without the little magnetic fields and so on and the current. And you can see on the BNC cable there, I'm assuming it's like a standard shielded cable there, it's actually got a break at one end. And that break breaks that loop. As soon as you don't have the loop, you can't induce a current in it. So you end up with the signal coming out of your signal source, you measure it, and there's physically no loop, so there's no induced current on it. If that break is really, really large, really physically really long, so you end up with effectively a bit of cable with no shielding, you can also pick up other signals, but assume the break is quite small and it will work quite nicely. Ferrites, if you've got RF type noise from switch mode power supplies, you can get a little ferrite, which is basically it's iron dust glued together. You can loop your cable a few times through that, and that is extremely effective at blocking RF. So if you know you're picking up RF from somewhere, you put ferrites on, usually where, well, ideally both ends of your cable, but certainly on the end where you're doing your measurements. Single point grounding, star grounding, don't make loops basically. So the only connection to ground, for instance, would be you could, depending on the equipment, you could unground that bit of equipment, make it floating. And so there's physically no, where it says P there on the left, break that connection, and then you don't have any grounding there. So what's known as star grounding, or single point grounding. Differential signal measurements, we'll come to in a moment. If you, in extreme cases, you can use some like optical isolation or transformer-based isolation. And the most important thing is don't ever take off the earth pin from equipment to solve this problem. Equipment, and again, unfortunately, based on reality, it is there for a reason. It is for, I would say it's for your, to satisfy your employer's liability, but it's actually there for your safety. So do not ever, ever tamper with it, unless you know what you're doing. So actually acquiring signals, so generally you've got analog coupling or DC coupling. DC is like 0 hertz or 0 up to something, and depending on your device, your AC is probably from a few hundred hertz or kilohertz up to whatever you've got. And often you find you don't have built-in 50 ohm loads on AC coupling on scopes and DAQ-cards. It depends on the device, but that's generally true. If you are using AC coupled system, make sure that any DC that's actually present is within the limits, because otherwise you then start to break things, because usually they'll get too hot. High frequency is often done with transformers. We've got a system running at CERN that is a bandwidth of hundreds of kilohertz. So to isolate the signal, we use small RF transformers that, I think the lowest frequency they pass is something like 40 kilohertz. But it's fine for our system. Digital signals, you can also use opto-isolation, particularly if you're connecting systems together that may be running at different potentials. So you can get a signal, transform it into some optical signal for the actual connection. And there are generally two categories of the signal connection. Again, all this is taken from usually the last pages of the NI datasheets. If my source is grounded, how can I measure that with the ADC? Okay, so this first one, generally on the NI datasheet, it doesn't have that little red loop showing the current. But your grounded signal source, your grounded measurement system, when they share a ground, you will create a ground loop. So think back to that other diagram. That's where your loop is coming in, and you're very open to interference, to picking up current on there. And the equivalent source there is, so you're measuring your voltage source, but you're also measuring this ground potential as well. And it can be significant, tens of millivolts, and often it picks up at 50 and 100 hertz. So this is okay if you've got a system that's generating your signal and measuring it probably in the same rack or the same chassis. You don't generally have a problem. When your signal is coming from the room next door or the rack over in the corner of the room, this is when you start to find the ground loops actually occurring. So how do you get around this? Okay, most of these ADCs have this pin called AI, or analog input sense. So this is like an alternative reference to ground. And it's very useful because what you do is, so you've got your grounded signal source and your measurement system is still grounded. But where the signal source on the negative, on the lower bit, goes across there, it's going to this AI sense, which is not grounded, it's isolated from ground. And that means your signals can then actually be measured and you don't get any ground loop because there's no voltage from the ground loop because you've broken the loop. That's what you've actually got to do. Most of these devices only have one AI sense pin, so it means all of your signals have got to come from the same source. There's not multiple AI sense pins. So it's okay if all your signals originate from the same place. Not so good if you've got them coming from disparate sources. The rule of thumb is single-ended measurements where you've got, you're using this, on the ADC. Make sure your signal is big, i.e. greater than a volt. Your cabling is short. Short cabling implies that your signal source and signal sinks are adjacent. And if they can actually share some common reference, some common ground. So floating sources, things like thermocouples, battery-based systems, and so on. It's an ungrounded source. So your equipment is probably earthed, but your output signal is not referenced to that earth. It has its own floating output. So you can do something like this. So this is single-ended input, but your analog ground, so you don't have a ground loop. The signal source, the ground loop is broken because it's not connected to that little earth symbol there. So again, you won't have a ground loop. So you can do that, but you can actually pick up noise on the cable shield. Careful routing of your signal source can help eliminate that. My preference is to do this or the next diagram. So this one uses the analog input sense, and you need to reference that to something, so you use resistors to ground. If you follow the instructions at the back of the data sheets, you generally won't go far wrong. So you've also got to be careful, what's the output impedance of your load there, of your signal source. If it's quite low, you can use a 10k resistor. When I say low, I mean in the order of ohms or tens of ohms. If your output impedance is very high, and you have a high impedance resistor, you then create a potential divider. So what you measure is not reality. So you need to know a little bit about what your signal source is to accurately choose a resistor. You can quite happily put megohm resistors in there. This is just taken directly from the datasheet, but from experience, megohms is fine. if you've got, if that's what you need. Again, differential measurements. If you want to avoid most problems with noise, ground loops, pickup and so on, differential measurements are the ones to do. So, and again, it's set up very similar to the way you do the analog sense, but whereas the AI sense is used for multiple channels, you now reference to ground, and you're using true differential measurements. The disadvantage is you can only use half the number of channels of your ADC card. It's, you have to make that trade-off of number of channels versus how much noise you can, or how much induced current you can actually withstand. Always use differential measurements for small signals. So, I mean, if you've got a thermocouple device, you've got tens of microvolts. All the thermocouple devices will be using differential measurements. We're nearly done. Some ADC parameters, Nyquist, you all know about that. Make sure your sampling rate is at least twice what your bandwidth is. Otherwise, you get aliasing. You've all done that. Some ADCs have anti-aliasing filters. I'd say many have anti-aliasing filters. And if you pay a lot of money for your card, you can get controllable ones. You can turn off the filter, which if you want to do oversampling, which is a good technique to use if you've got a bandwidth limited signal, you can do that. But generally, they also have an anti-aliasing filter on them. The resolution of an ADC, okay, again, you probably all know this. So, I mean, a typical card there, 16-bit ADC, 20-volt range. It's like 0.3 of a millivolt. But, well, okay, rule of thumb, if you want to adequately reconstruct your sine wave, you need about 10 samples or so per cycle. That's generally accepted to be the minimum. Not all the information, when I say information, in a sort of like a Shannon sense, if you don't need all of that, sample it at a lower rate, it's generally cheaper. The effective number of bits. So you've bought your ADC, someone said, we need a 14-bit ADC or 16-bit, whatever it is. The effective number of bits, you basically don't get quite what you've paid for. It's a measure of the effective number of bits, or the ENOB. It's a measurement of the dynamic range of the ADC. Once you actually add in the noise, distortions, and so on. Those of you that are into hi-fi, these kind of things are important. So there's a very simple formula for calculating this. It's the one that ENOB is the sinad minus 1.76 divided by 6.02. All of these numbers in decibels, by the way. And on the data sheet, so you would normally be given this sinad value. So as an example, and I've missed out a few steps of the arithmetic here. A typical device there. Once you take into account this, the noise and the distortion, you've paid for your 16-bit ADC, your 6251. But by the time you've got all the noise and so on taken into account, your effective number of bits is down to 13. It's in the order of, generally, it's in the order of 85% of what you've started with. So just bear that in mind. Oh, I'm out of time. I'm out of slides. I'm going to say thank you to a few people. My colleagues at CERN, because I gave this presentation in a slightly different format to them, and without exception, they all went off and checked their triggers and cabling, because I used the scenario there, that really happened. And they were having problems, but they didn't really know why. Now they know why all of their measurement problems were coming about. They had like T's and terminations scattered all over the place. It was a bit of a mess. And colleagues at Royal Holloway, particularly one chap who's now retired, but taught me loads. I have a recent company called Angara Technology, and we're looking to make an impedance-matched trigger and delay card, because we've realised in our work there is a big call for it. So we're actually developing one. We're looking to make it in C-RIO. If you're interested, because we haven't finalised all the spec yet, we know roughly what we want to do. If you are interested in this, just come and find me. it would be very useful to see if anybody else is thinking the same way we do. And that's it. So thank you very much. I don't know if there's time for questions, but no time for questions. If you want to talk to me, find me afterwards. I'll be around and about. Okay, thank you very much.